This is a data center that will use more electricity than the entire city of San Francisco. It isn't finished yet, and by the time it is, someone will have already announced a bigger one. Welcome to the Gigawatt race, the strangest, most expensive construction boom in modern history, and almost nobody outside the industry understands how big it's actually gotten. Let's get into it. A few years ago, a 100-megawatt data center was considered a genuinely massive project. Today, that number barely registers. The new unit of measurement is the gigawatt, enough electricity to power roughly 800,000 homes. And there are now more than half a dozen active construction sites in the United States alone targeting that scale, with some aiming several times higher. To understand how we got here, you have to understand what changed. For 20 years, data centers were built to store and serve information, websites, emails, streaming video. That kind of computing is relatively power light. Training and running large AI models is a completely different beast. It requires enormous clusters of specialized chips running constantly, generating so much heat that entire buildings have to be re-engineered around cooling rather than storage. The result is a construction typology that barely existed 5 years ago and is now consuming a meaningful share of the entire construction industry's capacity. So who's actually building these things, and how big are we talking? Let's start with the headline project, Stargate. It's a joint venture between OpenAI, Oracle, and SoftBank, with an eventual investment figure that's been put at $500 billion. The flagship site sits outside Abilene, Texas, roughly 1,100 acres, 8 buildings, and a planned capacity above a gigawatt just for the first phase. When fully built out across multiple states, the companies involved have talked about approaching 10 gigawatts of total capacity. For context, that's in the same ballpark as the electricity output of several nuclear power stations combined. Then there's Meta. Its Hyperion campus in rural Louisiana is being built for an eventual 5 gigawatts, spread across more than 3,000 acres. Mark Zuckerberg has publicly said the company is planning for tens of gigawatts of capacity this decade, and eventually hundreds of gigawatts over the long run. That's not a typo. That's the scale hyperscalers are now talking about in earnest. And then there's xAI, Elon Musk's company, which built its Colossus facility in Memphis, Tennessee in a genuinely staggering timeframe, reportedly around 4 months from groundbreaking to operational. A second facility, Colossus 2, is targeting a 12-month build-out to reach gigawatt scale. In an industry where permitting alone can sometimes take longer than that, these timelines are, frankly, absurd by traditional construction standards. Amazon, Google, and Microsoft are all doing versions of the same thing at similar scale, mostly with far less media attention because none of them have quite the same appetite for public spectacle as OpenAI or Musk. Combined, capital expenditure from the 4 largest hyperscalers hit over $400 billion in a single recent year, an increase more than 80% from the year before. And projections for the following year push that figure towards $700 billion. So why is this happening now, and why is it happening this fast? The honest answer is competition. Every major AI lab believes that whoever has the most computing power will have the most capable models, and whoever has the most capable models wins the most valuable technology race in a generation. That belief has turned data center construction into something closer to a wartime mobilization effort than a normal capital planning process. Nobody wants to be the company that didn't build enough compute in time. Before we get into how these things are actually built, it's worth understanding just how different the engineering challenge is compared to a conventional data center, let alone a conventional building. The first constraint is power. A gigawatt-scale campus needs a direct, dedicated connection to serious generation capacity, sometimes an entire new substation, sometimes a direct arrangement with a power plant. In some cases, developers have turned to on-site gas turbines just to bridge the gap while grid connections catch up, a workaround that's drawn criticism from environmental groups and regulators in more than one state. The scale of power draw is such that a single campus can rival the electricity demand of a mid-sized city, arriving all at once on a permanent basis with essentially no seasonal dip. The second constraint is cooling. Traditional data centers used air-based cooling systems, blowing chilled air across server racks. Modern AI training clusters generate so much heat per square foot that air alone often isn't enough. Many of these new facilities use liquid cooling instead, running coolant directly to the chips themselves, which requires a completely different plumbing and piping infrastructure than a conventional data hall. Water usage has become its own flashpoint, with several proposed facilities facing local pushback over strain on regional water supplies, especially in drought-prone states. The third constraint is speed of fit-out. Because the underlying chip technology changes so quickly, new GPU architectures arriving roughly annually, these buildings are essentially designed to be gutted and re-equipped every few years. That means the structural shell, the power distribution, and the cooling infrastructure all need to be built with a level of flexibility that a normal industrial building simply doesn't require. Contractors describe it less like constructing an office building and more like building a piece of infrastructure that happens to have a roof. Then there's the sheer physical footprint. These aren't single buildings, they're campuses, multiple structures, often each the size of a large distribution warehouse, connected by extensive underground power and data conduits, surrounded by substations, cooling plants, and in some cases, dedicated water treatment facilities. The Stargate site in Abilene alone covers roughly 4 million square feet across its 8 buildings. Meta's Hyperion campus in Louisiana spans more than 3,000 acres, larger than some small towns. And speaking of towns, that's where the story gets more complicated. These projects are overwhelmingly landing in rural and semi-rural areas, places with cheap land, available water, and crucially, access to power infrastructure. Louisiana, Texas, Ohio, Mississippi. But dropping a project of this scale into a small community creates real friction. Local reporting from communities near several of these campuses has documented spikes in housing costs as construction workers move in, damage to local roads from constant heavy truck traffic, and disputes over who actually pays for the new power infrastructure these facilities require. Some utility companies have adopted what's sometimes called a pay-for-your-own power model, structuring rate agreements so that the data center operator, not existing ratepayers, absorbs the cost of new generation and transmission capacity built to serve them. It's a reasonable-sounding compromise on paper, but residents in several of these areas say the disruption during construction and the permanent change to the character of their community isn't something a utility bill can fully offset. There's also a financing story here that's genuinely fascinating if you're into that sort of thing. Because these projects are so capital-intensive, hyperscalers have increasingly turned to joint ventures and specialized investment vehicles, rather than funding everything on their own balance sheet. In one notable arrangement, Meta partnered with an investment firm on a special purpose vehicle where the investment firm owns the vast majority of the entity, while Meta operates and leases the facility, with billions of dollars of the venture's debt sold on to institutional bond buyers. It's a structure that lets the tech giant get the compute capacity it needs without carrying the full asset on its own books, spreading the enormous risk across a wider pool of investors. Whether that risk is being appropriately priced is a question that's dividing analysts. Some point out that if AI demand ever cools, or if a cheaper way to train these models emerges, a huge amount of very specific, very expensive infrastructure could become stranded assets almost overnight. Others argue that the demand curve for computing power has consistently outpaced even the most aggressive build-out plans, and that the real risk is building too slowly, not too fast. So how does this all end? Nobody really knows yet, and that's part of what makes this such a remarkable moment in construction history. Total investment into data center infrastructure globally is projected by some analysts to reach into the trillions of dollars by the end of the decade, driven by well over 100 gigawatts of new AI-related capacity that the industry believes it will need. That's an almost incomprehensible amount of physical construction: steel, concrete, transformers, cabling, cooling infrastructure, being deployed at a pace that traditional infrastructure planning simply isn't built to accommodate. What's clear is that this isn't a normal construction cycle. It's an arms race, playing out in rural counties across America and increasingly around the world, funded by some of the most valuable companies on the planet, built faster than almost anything in the industry's history, and creating ripple effects, economic, environmental, and social, that the communities hosting these campuses are only beginning to reckon with. Whether the bet pays off depends on whether the AI boom driving all of this construction lives up to the expectations baked into every one of these gigawatt-scale blueprints. For now, the concrete keeps pouring, the transformers keep arriving, and somewhere, another announcement for an even bigger campus is probably being drafted right now. And as always, if you enjoyed this video and want more from the definitive channel covering the world's biggest infrastructure stories, make sure you're subscribed to Apex Infra.